Okay, so we had been looking at how you might store an image with a fewer number of colors, and we saw that you can throw away some data using subsampling. Your problem then is you either have to have bigger pixels or you have interpolation. And in the last class we looked at how you might reduce the number of bits required for each pixel by reducing the number of colors in the image. And so we saw you had palettes, and you can reduce the number of colors, but it can look bad at times. But one of the tricks we have to get away with having so few colors is we can use dithering. Okay, so we're going to look now, hopefully today we'll get through JPEG and GIF, but we'll start with GIF, just some of the features of GIF. I'm sure there are more than a few sketches online about nerds in the pub having a fight over whether it's GIF or GIF. Okay, so some people pronounce it GIF, some people pronounce it GIF. It turns out that the GIF people are technically right, but it doesn't make them cool. So the cool people call it GIF. I think in Ireland anyway it's still GIF. Okay, you get some people be GIF. You think it's GIF? Okay, just smack them. Okay. Now, so the main thing about GIF is that you can only have 256 colors. So you can have 8 bits per pixel at most. The compression is in itself lossless. Now, okay, GIFs suck, but that's because you went from 16 million colors to 256. There's your loss there. That's a fairly lossy process, no matter how you do it. But the actual process of compressing GIFs themselves, that per se is lossless. One color may be transparent in GIF, so you're allowed like one slot in the lookup table can be invisible, and you can see through it, and that can sometimes be useful. You can have a progressive option, I'll explain that, and you can have animated GIFs as well. So the way GIF works then, it makes it ideal for things like logos, where you have plain expanses all of the same color. So computer generated images or graphics, GIF is great for that. Anything that doesn't use too many colors. So, you know, a photograph of the Grand Canyon, lots of different subtle shades of different colors, not so much. Logo, yip-de-doo, no problem. So there may be scenarios where GIF is actually the best choice. It's tempting to think that something shiny and modern and new like JPEG is always the best choice. But for certain things, GIF is a better choice. Okay? Doesn't actually use run-in encoding. GIFs can have one transparent color. So the image there on the left has a transparent background, so you can see through it. So you can imagine if this was an image on, let's say you had a web page with a funky background, you can see through some of the GIF onto the background. So that's a feature that's useful on occasion. GIFs can be coded progressively. So ordinarily a GIF will read and will be displayed, excuse me, like you go, and again, you do the first line and then the second line and then the third line and then the fourth line of pixels and so on like that. But you can do progressive coding. And that was very useful at a time when internet connections were slow. So with progressive coding, you get an impression of the whole image before it's downloaded. So as I like to put it, at the halfway point in progressive coding, you can half see all of it instead of fully seeing half of it. So if we look here, this represents a progressive download. And so as the image goes, as the image downloads, it becomes more and more resolved. And eventually, so at the halfway point, you can half see all of it. So that's progressive coding. Okay. Whereas with regular download, at the halfway point, you can fully see half of it, as opposed to half seeing all of it. And the interesting thing is that it doesn't download any faster. Just the wait doesn't feel as long. So this was a thing you could do with GIF, and people did that typically in the early days of the internet, just because it made pages not so frustrating to wait to download. It's tempting, given in the world we live in now, to think that pages download instantly, but they don't. Okay, that's your normal download there. No, so that's progressive downloading. So you can do that with GIF. That's a useful feature. Hello. Okay. Thought there was more there. What else was I saying? Yeah, progressive option. Animated GIFs. You can do an animated GIF. You know this. There was a time I used to explain to people, you can actually do animated GIFs, but as you know, they're going through a bit of a resurgence again as a medium, as an art form almost. So you don't need to be told that, but that was something a lot of people didn't know a few years ago. But they're all the rage now at the moment. So if you want, inside in Photoshop, you can actually set it up to make your own animated GIF. That would be an interesting thing to do in the labs if you were interested. Okay, so that's GIF, also known as GIF by the right but not cool people. No. What we're going to look at now is JPEG. And JPEG is significantly more complex than GIF. It's much more modern as well. JPEG is quite new. So GIF was around a very long time, and JPEG stands for Joint Photographic Experts Group. So even pre-web, people started to realize that there was a need for some sort of a standard in order to transmit images from A to B. So pre-web, you would have had different computer systems, and they might have all had their own particular image formats. GIF was the only one really that was interchangeable, that would work well. Could you get that door actually? That could work well across different systems. There wasn't really a proper image standard. And so you might get an image from somewhere, and then you might have to get a program that would convert it from sun raster file format into whatever format. And it wasn't such a big deal because it's not like you had some global connection of computers all connected up together. That wasn't happening anyway. So pre-web, it wasn't such a big deal. But even before the web, in 1986, people started working on a standard. So that if you wanted to send an image from A to B, people at the other end would have the software that would be able to display it also. An early adopter of this kind of this scheme was the California DMV. They were one of the early sponsors of this. So you can imagine somebody has robbed a bank in Tennessee, and the police in Tennessee want to get their picture from California. They would have to fax it, and there was an interest in having a standard for images. So you have the Joint Photographic Experts Group. These are a bunch of people got together and they had meetings. And in 1992, they came out with ISO 10918-1. This is an ISO standard, ISO 9000. There's a standard for coding images. Now, it had a number of features that were important. It was capable of doing lossless compression. So JPEG can do lossless compression. Now, we don't associate JPEGs with lossless compression, but it is possible. But 99.999999% of the JPEGs out there would be using lossy compression. Okay? As you'll recall, the difference between lossy and lossless is that in lossy compression, the image you get back isn't an exact copy of the one you started with. So if you take an image, compress it, send it off, at the other end it gets decompressed, If the decompressed image is an exact replica of the original uncompressed image, it's lossless, otherwise it's lossy. And there are scenarios in which we're prepared to accept some loss, and in others, not so much. Okay? Now, once again, we're interested then in the cost-quality trade-off. And this is one of the things your assignment 2 is going to investigate. So as you reduce the quality setting in JPEG, how does that have an impact on the size of the file? And at what point are you getting good value? What point does the image still look good? When does it start to get bad? These are the things you're interested in. But the ways in which JPEGs go bad are very different from the ways in which GIFs go bad as the quality gets reduced. And we talk about the compression ratio. That's the original size divided by the compressed size. So if it started off being 5 megabytes and when compressed down it was 1 megabyte, you'd have a compression ratio of 5, or a compression ratio of 5 to 1. Typically with a JPEG, you're talking about maybe a compression ratio of 3 to 1. And everything holds up pretty okay at 3 to 1. But you can push the boat out or you can be paranoid depending. Okay? So obviously, if you have high quality files, they're going to be larger. If you have low quality, they're going to be smaller. So you can do the same with audio. If you're going to the gym, you could have 100 songs in high quality, or you could have 200 songs on your MP3 player in low quality, or you could have 400 songs if you wanted to push the boat out. Depends again on the situation. When we talked about the LAB color system, I mentioned that humans are significantly more sensitive to luminance than they are chrominance. So the lightness and darkness information is very important. The color information, we can tweak that a bit and still get away with it. So that's because humans have rods and cones in their eyes. So the rods are sensitive to luminance and the cones are sensitive to chrominance. And we have many more rods than we have cones. People believe that the ability to see color evolved much later in humans than and different parts of the spectrum evolved at different stages. Okay, so this again should look familiar to you, where we separate out the luminance and the chrominance information. Here I have an image in which I have separated the luminance and the chrominance information and then subsampled the chrominance information. And if we put the subsampled chrominance information back in with the original luminance, we see that here the chrominance has been subsampled a lot and we don't see much of a difference. So I showed you something like that with a picture of myself, I think, and we saw that at edges and things it starts to give, but you can really get away with quite a lot. And that's one of the things that JPEG does. So here there's a lot less color information in this image than in this. Now in fairness, this is a convenient example because there isn't a whole lot of color information in there to start with. So these are the steps then that JPEG follows. These are the steps that it goes through in order to compress an image. And there's quite a few of them. It's easy to see how each of them is reversible, but some of them will introduce some loss. And so we're going to look at those. So the first thing that JPEG does is it breaks up everything into 8 by 8 blocks. And for each block, it subsamples out the luminance and the chrominance, and it codes them separately. Now, JPEG uses some mathematical voodoo called the discrete cosine transform. And we don't need to know what that is. It's a whole bunch of maths. But what the discrete cosine transform does is it transforms information from the spatial domain to the frequency domain. And then it can transform it back down again with the inverse discrete cosine transform back from the frequency domain to the spatial domain. I just like to think of it as Star Trek, really. So it takes information and it beams it up, right? And do you know the way, like, an episode is just about to end, there's like 5 minutes and we still haven't solved the problem. Oh, they're all in the pattern buffer, we'll do ding, 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 and beam them back down and they'll be grand. Like, between being beamed up and being beamed down, where are the people? Well, they're like in the frequency domain, okay? So we can beam data up from the spatial domain to the frequency domain, and we can beam it back down again from the frequency domain to the spatial domain. But what's interesting is we can dick about with them a bit while they're up there in the frequency domain, and we can lose some of the information and get away with it. So if, for example, you were to take me in the spatial domain and reduce the amount of me by 10%, you know, I might be missing an arm or something, okay? Which wouldn't be satisfactory. However, if something is in the frequency domain and you reduce the amount of information there, it's not as catastrophic. So if you beamed me up to the frequency domain and then threw away 10% of me and beams me back down, you might go, oh, Colin, you've lost a few kilos there. You must have been going to the gym or something. You know, it's not like losing a whole arm, just, you know, shaved off a little bit. And maybe the color of my tie has changed slightly. So you can remove information when it's in the frequency domain without it being as destructive or being as damaging. So when you beam it back down then, it doesn't look so bad. So there's a bunch of maths there. So let's imagine that these were the values of the pixels. I'm going to talk you through the steps. Now feel free to zone out, but do it quietly. So the first thing we do is we subtract 128 from each of those values, which is all we've done here. And you could see how that's reversible. You could just add 128 to these values and you get back the ones that you started with. So that's a perfectly reversible thing to do. Each of these values then is going to have the DC, this block here of pixels or values. We do a discrete cosine transform on that. And we don't need to understand the details of the discrete cosine transform, but it gets us this whole bunch of numbers. And you notice the top left there's one big number, and then there's a bunch of other numbers. And you notice that, you know, up the top left, apart from the huge big one, even up at the top left, there's bigger numbers and there's kind of smaller numbers down the bottom right. And that's just the way the DCT has organized the information. But it's actually put the most significant information up in the top left where we can sort of get at it. So each of these values then gets divided by a number in this grid here. This particular grid isn't predefined. I got this from a textbook somewhere. This could be varied. Different coders might use that, do that slightly differently. And depending, of course, on how much loss you want to introduce, you could do a little of that or a lot of that. So here now, for example, that minus 415 is going to be divided by 61 to give minus 26. This minus 30 here will be divided by 11 to give minus 3. This minus 61 will be divided by 10 to give minus 6. This 27 here will be divided by 16 to give 2. Now this part of the process is lossy, because if I take that 2 and multiply it back again by 16, I'll get 32, will I not? It's not 27. So this part of the process isn't reversible. If I take minus 6 there and multiply it by 10, I'll end up with minus 60, not minus 61. So here we are doing what's called some coarse quantization. Okay, so all these things get divided, and that's the lossy part, and blah, 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 and that goes on. Okay, so we've done all that now, and we've got these values here. Okay, and then we list those values in this order. So we do like a zigzag order here. We go 26, minus 26, then minus 3, then 0, then down to that minus 3 and up and over. So we list them in this order. And if you look here at the values, there's the big one up here in the top left. And in the top left, turn that off now, whatever, please, it's very distracting. Up the top left there, those are bigger values. And in the bottom right, see all those zeros? So those zeros are going to be very easy to compress, particularly if you're going in this order, because you've got a whole bunch of zeros one after the other. So you can just say, okay, this is, minus 1, whatever, and then I've got, 20 zeros all together in a row. So it can be easy to compress those. So the data here then at the bottom is what ends up representing that block of images. Okay, so that's probably more detail than you need. I'd be prepared to concede that point. So each of these processes then is reversible, but of course this part here was lossy where we did that division, so we won't get back exactly what we started with. Interestingly, the way that's done there may even be unique to a particular chipset or to a particular camera. There's a discipline called image ballistics where you can analyze what parameters have been used to code the JPEG, and you might be able to conclude that that was taken with a particular kind of camera. So you can imagine all sorts of CSI scenarios where that might be useful. You find a JPEG and you can say, haha, that was taken with a Canon whatever, whatever, whatever. No. So, because of all that then, it turns out that JPEG is really well suited to natural images. So if you have photographs of the countryside, of people, things like that, it works great. Whereas JPEG was ideal for graphics and logos, where GIF was ideal for graphics and logos, JPEG is ideal for natural images. And that was part of the design brief. That's what it was meant for. So like I was saying, the discrete cosine transform there is the main thing. And when you introduce some loss in the frequency domain, when the thing comes back down again, when it beams back down again, it's not so bad. Okay, that's the point there. Now, JPEG is using 8x8 blocks of pixels. I think if you were to devise something like JPEG today, you might go for 16x16 blocks. But at the time, 8x8 was a lot of processing power to ask of a machine. And so JPEG isn't very good at preserving distinct edges. It's not great for graphics and text, particularly when you push the boat out in terms of the compression. So in this image here, there's lots of lines and things, fine detail, and that's exactly what JPEG is bad at. And if you zoom in really, really closely on a JPEG that has the compression set high, you can actually make out the 8x8 blocks. If I had my cursor here, you could even count them. I guarantee you those blocks there, if we counted the pixels, they're 8x8. And so if you have a line that's running through that, there's going to be a bit of chopping, a bit of distortion. And we're seeing the edges of those blocks there where we wouldn't want them. You see them there? So that's the main feature of JPEG. when the compression is turned up really, really high, we see those blocks. And they're 8 by 8 pixels. So any questions on that? So you have GIF, which can use up to 256 colors. You may or may not have to use dithering, depending on the situation. If your 256 colors are chosen well, you might be fine without the dithering, or you might not. GIF is great for graphics and logos wherever there's plain expanses of color. JPEG, on the other hand, is particularly bad at those. It's not great at preserving edges. So if you had the white background and red CIT logo at that edge there where they meet, you sometimes find if the compression is turned up too high that the color washes out. Some of the red goes into the white parts, some of the white goes into the red parts. It looks kind of just, it looks dirty somehow where there's different colors meeting. But JPEG is ideal for natural images, photographs of people, landscape, all sorts of things. It is a standard, so you code it in a particular way, and then any other device or any other program using that standard can read the image also.